there, welcome to video number 3 in the chapter 3 series about acceleration and kinematics. So in this particular video, we're going to be taking a short break away from this velocity time graphs and be looking at velocity vectors and sort of how we do vector addition and thinking a little bit more about how we sort of represent changes in velocities based upon their vectors. Now, this will help us kind of picture the idea between positive acceleration and negative acceleration, and it'll also help us practice some of the concepts of, like I said, vector addition and how vectors sort of work together in a representation. So again, this idea of adding vectors, the numbers that we're going to be using in this chapter are easy numbers. This isn't really about the math that's involved. It's about practicing using that conceptual skill of, like, what does it mean to say delta V, or what does it mean to add two vectors together, or to subtract two vectors for that matter. So again, it's just a foundational skill that we're sort of building on as we go, as we kind of continue working with that concept throughout the rest of the particular chapter. And semester. So we're going to take a look at acceleration, and the common phrase is about negative acceleration. Acceleration, we always know that as speeding up. A lot of times we use the phrase deceleration to mean slowing down. And that's okay. That's not a scientific term. We do tend to use the phrase negative acceleration. And so the question that students oftentimes have is the phrase negative acceleration synonymous with slowing down? Do those mean the same thing? The answer is no. But the whole idea here is to figure out kind of why they're not synonymous. And so how do we represent changes in vector quantities using vector diagrams? Arrows, basically, is what we're going to do. So the first thing is we want to make sure that we're kind of revisiting our basics here. When we're trying to calculate acceleration, we need to calculate change in velocity, delta V. How do we do that in a vector diagram format? Again, just using arrows. So when we're talking about vectors like acceleration and velocity and force and other things that we talk about later on in the year, we do need to kind of be in that habit of drawing vectors as having both magnitude and direction. Magnitude, remember, is the size of the arrow. And then direction is just which way is the arrow pointing. So that one's pretty straightforward. And when we add our vectors, we always add them in a way that we line our vectors up tip to tail. So this is when we're talking about drawing and representing vectors, that we always draw them tip to tail. A vector as an arrow is really an imaginary quantity. It's an abstraction that we are using. So it's just an arrow. It's really all it is. We can kind of take and manipulate these little arrows and move them around in ways that make sense for us mathematically, in a sense that the math works, but then the concepts also work. So this is that concept of tip to tail. One thing that is a little bit weird about vectors and vector quantities is that we really don't know how to subtract vectors. You can't say an arrow's this way and then how do you subtract something? It's a conceptually challenging thing to do. So what we actually say is, rather than subtracting vectors, we say we're actually going to add a negative vector. I know it's kind of weird to say that because you can't really go one way and then take it away again. It's a physical concept. Same like we're talking about, like forces. You can't take away force. You just have forces pointing in different directions. So when we're doing delta V, which should be subtraction, right? VF minus VI, how do we do that with vectors? So we're trying to find delta V between these two things. What we can actually do is talk about them in terms of changing changing the direction. So again, what we see, hold on, where's my pen? There it is. Sorry, there it is. If we're trying to do this sort of thing of subtracting VI, how do we go VF and then take away VI from that? I've had students say, well, you just kind of literally click on it and you move it here. And you can just take it away from there. So now you can lay them on top of each other. And that doesn't really give us the final idea that we want the delta V to it. So what we do instead, hold on, sorry, move that back out of the way, is we do that mathematical trick, is that subtraction, you can add a negative vector. Well, so if this is VI, what exactly is negative VI? And that's always well, what the heck could that possibly be? So I'm going to make a copy of my VI here. Negative VI, because we're talking about directions. Directions are simply opposite. So all I have to do is do that. And now it's pointing the other way. As long as they have the same size and opposite directions now, this second vector that we have drawn, where's my pen, is now negative. Oops, if I can get my pen, sorry. It's now negative VI. Okay, it's got the same magnitude, and it has the opposite direction. And again, this is the key part to adding vectors together, or subtracting vectors. We're going to take the negative of it and move it around. So now what I can do is I can take this vector and add them together and see what our difference is. Now, why does this matter? Because we need to add them up tip to tail. If we put them in this original format where it's the blue one and then the green one, they add up this way, but this gives us the sum of VI plus VF. We need to add them up so that we've got VF plus negative VI. So here we have them lined up tip to tail. There's their VF, and now we're taking away, in a sense, what VI is. So now we can see what our VF is. Our VF always goes from the start of the first one to the end of the second one, from here to here. So this would mean that our VF plus VI, this would be delta V. Okay, so again, I know it's a little bit hard to do this. I'm going to do this with some numbers in the next few to kind of show some examples of this. But remember, we're starting with VF, so that means our resultant vector has to start at the tail of this one, and then it ends at the tip of the second one, which is right here. So that's why we have our delta V is in that particular spot. Now this shows us the magnitude, how big delta V is, and it shows us the direction that it's pointing towards, the same direction as VF is. So let's show some numbers. It'll make it a little bit easier to see. All right, so if we're trying to figure out what delta V is, and then we can use that to calculate acceleration, what's the magnitude and direction of acceleration of an object that goes from 10 meters per second to 15 meters per second in 1 second? Okay, so again, these are both positive. So here's our VI. Say this is VI is equal to 10, and again, plus 10. And then our VF, like that, VF, and this is equal to plus 15. So what was our actual acceleration, right? We started at 10, and then we ended at 15. Now, you know this logically. It means it sped up. It got faster. So that means that our acceleration has to be sort of pointing this direction, right? That has to be the direction that A is pointing, that way. I know my video is backwards, so I'm pointing the wrong direction on the screen. But it has to be going the same direction. It's speeding up. It's got to be something that's kind of pushing it that same direction. So how do we draw this? Well, delta V is really easy, right? VF minus VI, or VF plus negative VI. So the number is super easy. It's 15 meters per second plus negative 10 meters per second. Again, I'm doing this as the addition of a negative rather than subtraction, because that's really what we're doing in the vector quantity, not just mathematically. So you can tell what the difference here has got to be. Well, the difference here has got to be not just 5, but positive 5, right? 15 minus 10. So our vector change, or change in velocity, is plus 5 meters per second. So let's see if we can draw this. Okay, VF is going 15 this way. There's VF. Now we're going to add plus negative VI. So I'm going to change it, make it the same size, but I'm going to reverse the direction of it. So now it's coming back this way. So like that. So that's our negative VI. And that means that our delta V, again, starts at the tail of the first vector and ends all the way at the tip of the second vector, which is right there. So it starts here and ends here, points that way. So this has got to be our delta V, and it would be in the positive direction, the same direction as VF. So it's plus, same direction, sorry, plus 5 meters per second. Again, because this is plus 15, this is negative 10. Okay, it's just getting used to representing it. I know it feels like, God, this is a lot of work for simple math. I know. But as we get to more complicated situations, you got to kind of have this idea about how we add these things together for it to make sense. So again, our delta V here was in the same direction as VF, right? Going that same way. That means our acceleration is also in that same direction, because if I know our delta V here was positive 5 meters per second. And we know what our time was from our original problem, plus 1 meters per 1 second. That means our acceleration is 5 meters per second squared. Positive. Again, going in the same direction, speeding up. Okay, let's take a look at a couple other examples. Again, they start off easier, they get a little bit more complicated. All right, so what about our magnitude and acceleration for an object that goes from 15 meters per second to 10 meters per second? Okay, VI is 15 meters per second. This is VI, 15 meters per second, right, starting. And then our VF is this. VF is plus 10 meters per second. Is it speeding up or slowing down? You guys know this, it's slowing down. So something's got to happen. Our delta V has got to be on the negative side. So again, how does this turn into delta V on the negative side? How is it slowing down? All right, remember what we are doing. Delta V is VF plus negative VI. So we're going to take our VF, which is 10. So this is plus 10 meters per second. And now I'm going to do my VI backwards. Again, negative VI is going to go this way, and it's going to be negative 15 meters per second. So the top one was VF. This is VF. This one is VI. Again, final minus initial. So now which way does our resultant vector go? Okay, our resultant vector starts at the beginning of the first vector, which is VF, and ends at the tip of our second vector, which is VI. It's going this way. So now you can see it starts at the tail and ends at the arrow side, so it's pointing that direction. So now we can figure out what the magnitude and velocity is. Plus 10 and minus 15 gives us a negative 5 meters per second. Negative sign means it tells us it's going this direction. Positive sign goes to the right. Negative sign goes to the left. So that gives us the sign and the magnitude and direction of it. So therefore, our acceleration here, our acceleration would be negative 5 meters per second in 1 second. So it's negative 5 meters per second squared. Again, our negative acceleration in this case tells us that it is slowing down. Our velocities were positive, going to the right. Our acceleration is negative, going to the left. So here we have a case where VI is going this direction. VI is going this direction. VF is going this direction, but our acceleration is going that direction. It's negative. Again, pointing opposite directions. This becomes important. Okay, let's do a next example here, a couple more. Okay, magnitude and direction of acceleration of an object that goes from negative 15 to negative 20 in 1 second. So now we're kind of throwing some negative signs in here because this is where it starts to get a little bit more challenging to it. So here we've got VI is going this way. Here's VI, and it's negative 15 meters per second. And then VF is a little bit longer, right? VF is now going negative 20 meters per second. So if we're going to do delta V, we have to do VF plus negative VI. Okay. So VF goes this way. Okay, there's our negative 20. And then VI, we're going to add it tip to tail, and we're going to flip the direction of it. So now we're going to go back this way, 15. So we're going to make this plus 15 meters per second. Okay, so now where does it go? Our final resultant vector starts at the tail of the first vector and ends at the tip of the second vector. So that means it's going this direction is the way that it's going. So now we can kind of see our magnitude here, and we know the direction of it. Direction is to the left. So that means it's negative 5 meters per second. Now, what does that mean in this case? It's going from negative 15 to negative 20. Okay, so what? How is that even possible? All right, if we've got VI is going this way and VF is going this way, it's longer, right? So there's VF. And our acceleration is going this way. All three of them are going the same direction. Now, again, this is negative VI. Remember, it's going the wrong direction, right? But VI and VF were both to the left, and acceleration is to the left. This means that if they're consistent, it's speeding up. Okay, it went from negative 15 to negative 20, just in the negative direction. So going west instead of east, something along those lines. Okay, All right, let's do a couple. We got 2 more, I think, to go, and we'll wrap through this up. So walking through it, this is one of those ones where it'd be a good one for you to stop and pause and see if you can draw these vector models and see if you can make sense out of this. So here we've got one that's going acceleration from -15 to -10. Is it speeding up or slowing down? Is it getting more extremely negative, or is it getting closer to 0? So VI, there it is, -15. There's VI, -15 meters per second. And then VF, a little bit shorter. VF is -10 meters per second in 1 second. So speeding up or slowing down. Okay, delta V is VF plus -VI. So it means I draw VF first. Okay, VF, and again, -10 meters per second. Then I draw my VI tip to tail facing the opposite direction. So now I got to go VI this way, and it's 10, 15. So there's VI, and this is plus 15 meters per second. So how do we draw our resultant vector? Again, starts at the tail of the first one and ends at the tip of the second one. So it's going that direction. So this is now our delta V is going this way. All right, well, it's to the right on the screen. So our delta V here is going that way. Even though our initial velocity was to the left and this other velocity is to the left, how can our delta V be to the right? Again, this is a negative direction. It's flipped itself around. So remember, VF is -15, right? And this is plus, -10 plus -15. What's our answer going to be here? Plus -15. Yeah, we got to switch that around. I have to change the sign of this. -15, which is positive 15. There we go. It gives me a final answer of +5 going to the right. That's what that means. Okay, again, they're going opposite directions. So VI is to the left. This is VI. VF is to the left, VF, and our acceleration is to the right. Okay, if they're going opposite directions, that means that they are slowing down. We went from -15 to -10. It's approaching 0. We had -15, and then we had -10. So our acceleration is actually the opposite direction. So it's negative acceleration in a sense. So it's slowing down. It's weird. I know it's weird. All right, I think I have one more. 2 more. 2 more. Okay, there we go. So last one. What's the magnitude and direction of acceleration of an object that goes from +10 meters per second to -10, or -10 meters per second to +10 meters per second in 1 second? Okay, again, now we're really changing direction big time, not just speeding up in the same direction, but truly changing direction because one's a negative and one's a positive. So we've got VI is, -10 meters per second, VI, -10, and then VF is +10. So how do we draw this? Delta V equals VF plus -VI. So we're going to flip that one around. So VF is going this way. So that's +10. Okay, that's VF. -VI. Okay, so hold on. They get placed tip to tail. So now instead of pointing to the left, this is going to be pointing to the right. And we can just put it right there like that. So this is VF. This is -VI. This is also +10. This means that our acceleration, our resulting delta V, starts at the tip of the tail of the first one and ends at the tip of the second one. So that means this now, literally added together, is our acceleration. This acceleration is huge. This is why accelerations of 2 things that are hitting head on or that are changing directions are such massive directions, such massive changes in a lot of things like energy and stuff like that. So this one, not only does it changing direction, you can't really say it's speeding up or slowing down because the numbers are the same, but it's going the opposite direction. And that's a big, big, big change in terms of it. So what do we have in terms of this? We had VI was this way, VF was this way, and acceleration ended up being that way, quite a bit bigger than either the two either the two original ones. So again, it gives us an idea of what the direction is, and the acceleration is in the same direction as the final velocity. So again, that makes a big difference in terms of where it's going around. So anyway, just some different ways to visualize what delta V is and how to visualize what the direction of acceleration is: positive acceleration, negative acceleration. One of the things to keep in mind is that, again, negative acceleration is not speeding up and it's not slowing down. It simply means it's going the opposite direction from the velocities that are involved. So if you have negative velocities, negative acceleration means you're speeding up. If you have positive velocities, negative acceleration means you're slowing down. It depends on whether the signs match, and that's really the important part of this. So when you compare the signs of your delta V, the change in direction, to those two, if they have the same signs, if VI and VF are positive and delta V is negative, it's slowing down. Conversely, or same, if you want to do it, if VI and VF are negative and delta V is positive, that means it's also slowing down. It's when the signs of them are different that we actually get the case of slowing down. So you get that change in velocities is the key part. Why can I not get my pen to go right? So if VI is, if these guys are positive and this one's negative, when they're different, it is slowing down. When they are the same, positive, 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 it's speeding up. Or negative, 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 it's slow. It's speeding up the other way. There you go. So again, if they match, speeding up. If you have different signs between your velocities and your delta V, it's slowing down, approaching zero. So again, it's definitely kind of a weird thing. Trying to get used to drawing these in terms of vectors and vector addition is a little bit different. Keeping track of those negative signs and being really respectful that negative signs are simply directions, east, west, north, south, rather than forwards and backwards can help. Okay, there you go. So that is sort of trying to visualize what velocities look like as and acceleration looks like as vectors. I'll see you in the next one, guys. Bye.